My dear student, today I will be talking about Lebesgue's monotone convergence theorem and another theorem regarding non-negative measurable functions. So we will be using Fatau's lemma, which we discussed in the last lecture, in proving this theorem. So this is the statement, Lebesgue's monotone convergence theorem. Lebesgue's monotone convergence theorem. So let Fn be a sequence of non-negative measurable functions such that when you evaluate the functions at the point x, you get a sequence of real number. So this is a sequence of real number, and this is sequence of function. This is sequence of real number is monotonic increasing for its x. That means f1 of x is less than equal to f2 of x less than equal to f3x, like that. It is monotonic increasing. And then suppose this sequence also converges to the function f, that is limit n tends to infinity fn is equal to f. Then the conclusion of the theorem says that integration of the limit function is equal to limit n tends to infinity integration fn dx. Okay, integration of the limit function is equal to, now fn dx is a real number after integrating. So you know, definite integral, if you take up definite integral, it is a sequence of real number. For that sequence of real number, you take limit that is equal to the evaluation of the integral of the function f. So this is the monotone convergence theorem. So we will be using Fatau's lemma in proving this theorem. Now, so since limit of the sequence is equal to function f, then by the definition, limit infimum fn is equal to f. So if the sequence has a limit, then limit infimum is exactly equal to limit of the sequence, that is f. This is what we have. Then let us use Fatau's lemma here. So Fatau's lemma says that what? This is Fatau's lemma statement. This is the Fatau's lemma. Limit infimum fn dx, integration is less than equal to limit infimum integration fn dx. This is Fatau's lemma. But limit infimum fn is equal to f, no? So this quantity is exactly equal to f. So integration f dx is less than equal to limit infimum integration fn dx. This is what we have. No, this is inequality number 1. This is inequality number 1. Also, the function is, for its x, the sequence of function is monotonic increasing. Fn x is monotonic increasing, means as n tends to infinity, you get f, and f, will be the supremum. That means f will dominate, the member of the sequence. That means f is greater than or equal to fn for its n. Alright, since it is monotonic increasing, the limit, that is when n tends to infinity, will be greater than any other member of the sequence, fn. So this is true for every n going from 1 to infinity. So we also know that if f is greater than or equal to fn, then integration of f dx is greater than or equal to integration of fn dx. This we know it. So that means if you have this quantity, so many, for f1 also you evaluate, f2 also you evaluate, f3. So is one of them is less than or equal to f dx, integration f dx. So then from this quantity you take limit supremum. That means from that limit supremum also this quantity will be greater than. Okay, limit supremum also this quantity will be greater than. This is inequality number 2. So from 1 and 2, what do you get? From 1 and 2, we know that limit supremum is always greater than or equal to limit infimum. So from 1 and 2, what do you get? Limit supremum is less than equal to integration f dx, but this one is less than equal to limit infimum fn dx. This is from 1 and this is from 2. This is from 2 and this is from 1. Okay, so you get this combined inequality. But what we know is that limit infimum fn dx is always less than equal to limit supremum fn dx. Because of this, what? These three quantity, this one, and this one, they must be equal. Okay, and then when limit supremum is equal to limit infimum, we just say that that is limit. All right, so instead of writing 2 limit supremum fn dx, limit infimum fn dx, so since they are equal, the equal value is called just limit integration fn dx. So integration of f dx is equal to limit integration of fn dx. This f is limit fn. Okay, so this is the conclusion of the theorem, hence proof. All right, this is called Lebesgue monotone convergence theorem. All right, this is very important one. So if the function, if the sequence of function converges to the limit function f, then integration of limit function is equal to integration limit n tends to infinity integration of fn. All right, so this is what we have for Lebesgue integration, but this is quite different from Riemann integration we did in the first semester. For Riemann integration, the convergence should be strong enough, that is uniform convergence. Okay, so this is one of the important differences between the Lebesgue integration and Riemann integration. In case of Lebesgue integration, if the sequence of function converges to the limit function f, the integration of the limit function is equal to limit n tends to infinity integration of fn dx. Okay, this is, you have to remember the difference between Lebesgue integration and Riemann integration. All right, so next is another theorem. This is also very important one. The statement of the theorem says that let f be a non-negative measurable function. Okay, so any non-negative measurable function, then there exists a sequence of measurable simple function. So phi n, I told you earlier also, phi n denotes, in this unit, phi denotes simple measurable function or measurable simple functions. Okay, so this is a sequence of simple measurable functions such that for each x, this converges to f of x. That means what? This arrow up means the sequence phi n x is increasing and it is converging to the function f of x. All right, so what is the conclusion of the theorem? For every non-negative measurable function, there exists a sequence of measurable simple function which is monotonic increasing and converging to the function f. All right, so this is one of the important theorem in measure theory. So now, yeah, let us do. The construction is little bit tedious, but I will give you simple example to make you understand easily. Let us see. For each positive for each positive integer n, let us divide let us divide the range of the function f or domain of the function like this. For each positive integer n, define enk by this equation. So what is enk? Enk is the set of point x such that f of x is less than equal to k divided by 2 to the power n, but it is still greater than k minus 1 divided by 2 to the power n. So this is those set of point x satisfying this inequality, that we call it enk. All right, then since the function f is measurable, this set enk is also a measurable set, that you already know it. Okay, so enk is defined by like this. So what is k? K is running from 1 to up to n times 2 to the power n. All right, k is running from 1 to up to n times 2 to the power n. Then also you define fn by this formula, or by this one. Fn is equal to what? This is a set of point x such that f of x is strictly greater than n. Alright, so what is fn? This is collection of the point x such that f of x is strictly greater than n. Okay, and then you put phi n is equal to like this. Phi n is equal to, then phi n is a simple measurable function, or phi n is a measurable simple function. Okay, by definition it is the linear combination of characteristic function, so therefore phi n is a simple measurable function. So let us see how we define phi n. Let us draw some diagram, a simple one. When n is equal to 1, let us try to do for n is equal to 1, and then we'll do, and we'll take the simple function. F is a simple function. F of x is equal to x, that is y is equal to f of x is equal to x, the straight line function. Let us see. This is your xy plane. This is your xy plane. The function is the function has, this is f of f of x, this is equal to x, or y is equal to f of x, this is y axis, and then this is x axis. Right, so let us see. This is your function, and suppose this is 1, this is 1, this is 0, 1 is here, and then 2 will be here. Right, 2 will be here. So what we have then, if you take n is equal to 1, then k, if you take n is equal to 1, then k can take value from 1 to n into 2 to the power n. Right, so k can take 1, then n 1 to the power 1 is 2, no? So k can take values like this, 1 and 2. Alright, so when when k is equal to 1, when n is equal to 1, e1 1 is how much? E1 1 is equal to, so k minus 1, k is equal to 1, k minus 1 is 0, and then this is strictly less than f of x. Okay, and this is less than equal to, k is 1 divided by 2 to the power n, to the n is 1, it is like this. Okay, so your e11 is equal to 0.x such that this inequality holds. Alright, then what about e12? E12 is how much? E12 is how much? And this is equal to x such that f of x, it is strictly greater than 1 upon 2, and this will be less than or equal to 1. It will be like this. Alright, so this is your u112. Then what about n is equal to 1? What about f1? We define also f1. F1 is equal to x such that f of x is strictly greater than 1. Alright, so what is, then you define phi is how much? Phi 1 of x is equal to, this is summation, k is running from 1 to 1 times 2 to the power 1, this 2, then and k minus 1 divided by 2 to the power 1. Right, characteristic function e, and the first one is 1 x. Okay, plus you go on, then what is, So here n is 1, then characteristic function e f1 x. So it is like this. So then what is e11 according to this, this function, that is y is equal to x. So what is e11? E11 will be when the function f of x is less than half. Okay, so less than half, half is here. All right, so half is here, 1 is here, half is here. So value of the since function is y is equal to x, this must height is also half. Okay, all right. So in that situation, the value of the function is equal to phi 1, x is equal to how much? If it is in this set, this is your e11, this is your e11, and this is your e12, like this. This is e11, e12. So if x belongs to e11, the function is equal to 0, because 1 minus 1 is equal to 0. This part is also 0. If it is in e11, it will not be in f1. So this part, this is 0. If the function, if the point x is in e11, then the value of the function phi 1 is equal to 0. If it is in e12, the value of the function is half. It is half. Sorry. It is half, like this. Okay, the function takes this value. All right. So beyond that one, that is, if x is more than, then the value of the function is, if x is more than 1, the value of the function is equal to how much? It goes up to infinity, like this. All right. So this is, from 1 to up to infinity, it is equal to f1. Okay, so your phi 1 is like this. All right. So when n is equal to 2, what do you get? When n is equal to 2, what do you get? Let us see. If n is equal to 2, the k can take value from 1 up to 2 times 2 to the power 2, that is 8. Then k can take value, k can take 1, 2, 3, 4, 5, 6, go. 6, 7, 2 into 2 to the power 2 is 8. So 8. All right. So k can take values like this. All right. So in that situation, what you have, in that situation, this is your function. Now let us change the color. So in that situation, the domain, the function domain is, again, so this is n is equal to 2. This is 2, no? This is 2. All right. So you divide this one into 2. This is 1 by 4. This is 1 by 4. All right. This is, so earlier this is half. This is half. And then 1 by 4. And this is how much? This is 3 by 4. This is 1. Then you divide this one is also. All right. You divide this one also like this. You divide this one. So the new function will be like this. In this part, this will be what? This will be e21. Okay. And this part 1 by 4 up to half, it will be what? This will be e22, and this part will be what? e23. It goes on like this. All right. So this is just the refinement of the earlier domain. All right. Then you define phi 2. Phi 2 is the function. This is equal to summation k running from 1 into 2 times 2 to the power 2 is 8. So k minus 1 divided by So 2 to the power n is 2, no? So this is 1. Then characteristic function e nk plus n times characteristic function fn. So here n is equal to 2, no? So you can replace this 2, and this is 2, you know, this is 2, like this you can replace it. So in that situation, you know, the domain is now it is subdivided. Earlier it is e11 is up to here, from 0 to half is e11. In this portion phi 1 is equal to 0. Now the portion, this domain from 0 to half is divided into two parts, from 0 to 1 by 4, then from 1 by 4 to half. Okay, so from if x belongs to, you know, if x belongs to e11, then x is either in e to 1 or e to 2. So this first part is e to 1 and the second part is e to 2. So if it is in, if x belongs to e11, what is phi of x? Phi 1 of x is equal to, you know, 0. All right, if x belongs to e11, phi 1 of x is equal to 0. Right, if x belongs to e11, then x is either in e to 1 or e to 2. If it is in e to 1, then phi 2 is equal to what? Phi 2 of x is equal to 0. If it is in e to 2, what? Then phi 2 of x will be, you know, 1 by 4, and this is 1 by 2 to the power 2 when n is equal to 2. Okay, so this is the thing. Then from here, what do you see? From here you see that phi 1 of x, you know, it is less than equal to phi 2 of x. The simple function we define like this, it is increasing. Likewise, phi 3 will be greater than phi 2x. Okay, all right, phi 4 will be greater than phi 3x, like this. So you have a sequence of increasing simple measurable function. All right, so this is the idea. Why it is increasing? Because you are subdividing, you are refining, you know, this dissection of the range of the function. Okay, you are dissecting. Okay, so this is the, you know, earlier it is from 0 to half, now it has been converted into two parts, 0 to 1 by 4 and 1 by 4 to half. In 0 to 1 by 4, the earlier function phi 1 is 0, and the second function phi 2 is also 0. But in the second part, 1 by 4 to up to half, the earlier function is still 0, but, you know, the second function phi 2 is equal to 1 by 4. That means this is the simple function. You know, the earlier function is black one. All right, so this is black one. Let me tell you. So phi 1 takes 0 in this part, you know, 0 in this part, and in this part it is, you know, from half to 1 it takes the value this one. All right, from 1 to up to infinity it takes this one constant. Okay, but, you know, this one, the phi 2 takes, you know, from 0 to 1 by 4 it takes 0. Okay, this part from 1 by 4 to half it takes 1 by 4, like this. Okay, this is 1 by 4. From half to 3 by 4 it takes, you know, this half value. This is the value. From 3 by 4 to 1 it takes this value. Okay, that is, this is 3 by 4 it takes. From 1 to up to here it takes this portion. Okay, so it goes on like this. All right, so from here it takes like this. All right, this is simple function value. This much height, this much height. Okay, so this is you know, this is the thing. You know, what I want to tell you is that phi 2 is greater than phi 1. Similarly, when you take n is equal to 3, you will again subdivide this part. This is smaller one, it will divide it two times, like this. Okay, so here in the second case, here it is 0, no? in this area it is 0, but in the third step it will not be 0, it will be 1 upon 2 to the power cube, that is 1 by 8. So in that way phi 3 will be greater than phi 2. Okay, phi 4 will be greater than phi 3, like that. So by this construction you are getting a sequence of, a sequence of simple measurable function. All right, and then again in the second step, let us see. In the second step, this is your function, in the second step this is the function value. This is the it takes function value when it takes point from here, but the simple function phi 2 takes this constant value, that is this one. All right, 1 by 4. So then what is the difference? The difference here, it is at this point the same value, at this point this much height difference is there. The maximum difference phi f of x and phi 2x happen to be this much. Okay, this much height. All right, this is suppose 1 by 2 square, it will be 1 by 2 square, 1 by 4. That means what? Phi 2 x f of x, its difference modulus will be less than 1 by 2 square, it is 1 by 4. If it is 1, it will be 1 by 2. If it is 3, then it will be 1 by 2 cube, like this. All right, so that means was as n tends to infinity, their difference is lesser and lesser. You can see it graphically also, you can see it graphically. Okay, earlier the difference was this much height. So if you take n is equal to 2, it becomes 1 by 4. Here it is half. All right, so it is like that. It is like that. You can practice, you can draw the diagram and try to understand what I am explaining. The construction is little bit difficult. So if I take the simple function y is equal to f of x is equal to x, then it is easier to understand, and I have explained, and that is how we construct this sequence of function phi. Now from this construction, what you have to understand is that phi 1 is less than equal to phi 2 is less than equal to phi 3, like that. That is, you have a sequence of increasing simple measurable function. Okay, and also in the nth step, difference between f of x and phi 2x, phi n x is less than 1 by 2 to the power n. So this is what we have from our construction. Yeah, so this is for the finite case here. So this is what we do. So next, let us go back to our note. See, so this is how we define the set and then the simple function like this, and then I have already explained. Then the function fn are simple measurable function. This is quite obvious from the definition. Also, since the dissection of the range of the function f giving phi n plus 1 is a refinement of that giving phi n. Okay, I explain you this is a refinement. It is easily seen that phi n plus 1 is greater than or equal to phi n x. That means this is monotonic increasing for its x. This is monotonic increasing for its x. All right, so if f of x is finite, then what? Since it is finite, it will be less than some sufficiently big positive integer. All right, it cannot be more than this one. It will be less than or equal to this one. Finite means like that. Okay, so once it is less than m, then it will be strictly less than m plus 1, m plus 2, and goes on. For every positive integer greater than m, it will be less than, the function's value will be less than that one. For some suitable integer m, okay, function finite means you will be able to find some suitable integer capital a small m such that f of x is less than equal to m. That means strictly less than m plus 1, strictly less than m plus 2. It goes on like that. So what, according to the definition of the set fn, so it follows that x belongs to fnc. What is the definition of, let us see, what is the definition of the set fn. So fn is defined like this. Fn is defined like this. It is a collection of point x such that f of x is strictly greater than n. This is your definition Fn. All right. So that means what? If the function is finite, what happens? Function is finite, then that function f of x is strictly less than equal to m for some suitable m, then it will be strictly less than m plus 1 and goes on like this. All right. So that means what? F of x is strictly less than or equal to n for all n greater than or equal to m. So that means if f of x is less than n1, that means what? X belongs to complement of fnc, no? All right. If f of x is less than or equal to n, then x belongs to complement of fn. This is true from the definition, straightforward. So that is what, let us see. Yeah. So it follows that x belongs to complement fnc for all n greater than or equal to m. All right. So in that situation, as I explained you earlier, difference between f of x and phi n x will be less than or equal to 1 upon 2 to the power n. This is true for all n greater than or equal to m. So that means if n is more than m, this happens. That means when n tends to infinity, sufficiently greater than this term is 0, that means this sequence phi n x converging to f of x. So that means what? Phi n x is converging f of x, and this is monotonic increasing. So increasingly converging toward the function f of x. This is the case when the function f of x is finite. Okay. If the function is finite, now we are able to show that the sequence of simple measurable function phi n is monotonically increasingly converging to the function f of x. So this is what we have done for the finite case. Now the function is infinite. Let us see in the case when the function is infinite, that means f of x is equal to infinity. In that situation, f of x is equal to infinity means f of x is greater than any positive integer. All right. Since it is infinity, it is greater than any positive integer. This is true. That means what? If f of x is greater than n, that means x, by definition of capital Fn, x belongs to Fn for all n greater than or equal to 1. That means what? X belongs to Fn for all n greater than or equal to 1. That means what? X is a member of is Fn. No? That means x is a member of the intersection n going from 1 to infinity Fn. Right? So that means what? If x, if x is a member of capital Fn, so according to the definition of the phi n function, this will be equal to n for all n greater than or equal to 1. Right? So that means what? The simple measurable function takes value n. Okay? Whenever f of x is equal to infinity. All right? So that means what? This is quite obvious that this phi n x is equal to n converges toward infinity. Okay, in this case also the sequence phi n x is also converging toward infinity, and it is monotonic increasing. This one, phi n plus 1 is equal to n plus 1, phi n plus 2 is equal to n plus 2, like that. So it is increasing and it is converging toward infinity, and that is the value of the function f of x. Okay, so in both the cases, finite and infinite cases, now we are able to show that the sequence of simple measurable function we constructed is increasingly converging toward the function f of x, and this is what we wanted to prove. So this much I want to give you today. All right, so you watch it again and again, and then you can copy the note, and then if you have some confusion, I told you again and again, so don't forget to talk to me and clarify your doubts. Okay, thank you very much.